Good afternoon. Welcome to Purdue University and the CERIAS Security Seminar. Our speaker today is Professor Chip Killian, first-year assistant professor here in the Purdue Computer Science Department, recent grad from University of California, San Diego. His talk today is titled Mace, Systems and Language Support for Building Correct, High-Performance Networked Services. Chip?
Thanks. So my research is, as he said, it's on how do you build correct high-performance distributed or networked services, and so where I sort of meet security in this line is trying to keep bugs from getting into the code in the first place so that people have nothing to exploit. So when I talk about a distributed system, right, this is a fairly heavily used term, so we'll first talk about what I mean when I say that. I actually have a very broad class of system in mind when I talk about a distributed system. So this includes things like the stock exchange, where you have computers talking to other computers, executing buy and sell transactions in order to keep the market going. And this is going to be a distributed system. Then there's a commuter train system, where you have a distributed system which is monitoring where all the various trains are, as well as making sure they don't collide with each other, routing them on the different tracks, keeping them in line. So there's a distributed system which is monitoring this. I'm also talking about things like the telephone network. Right? There's a very complicated set of telephone long-distance switches which interconnect the telephones all over the world, and when you make a phone call, we're routing communications from one telephone to another telephone through a distributed system. This will also include air traffic control centers. Right? Airplanes transmit requests to the air traffic control centers, who will route the planes through the airspace to make sure they don't collide with each other, send the route request back to the plane so that they can then fly. That's a distributed system because you have data which is starting in one place, it's being shared with other places, other computers elsewhere, and they're working together to accomplish a goal. This will also include trauma centers. More and more these days, trauma centers are also being run by distributed systems. So, for example, they'll install a main computer which has the job of farming out tasks to subcomputers to execute diagnostic tests. So the doctor comes in, they ask for some diagnostic to be performed, it gets farmed out to some subsidiary computer, which gets the result back to the doctor. Again, this is going to be a distributed system. And then finally, everybody's favorite voice over IP protocol, Skype. Many of you have probably used this to talk to friends around the country, around the world. This is actually a peer-to-peer type of distributed system where nodes will communicate through other third-party nodes in order to establish computer-based phone calls. So this is also a very big class of distributed system. I think this one has lots and lots of users. But these aren't all just distributed systems. These are, of course, all examples of flawed distributed systems, or systems which have failed, sort of in many cases, quite gloriously. And when I say gloriously, I mean they make the news, and they make the news in a big way. Right? When the stock market has a problem, it's a big news item. So in this case here, the computers which were monitoring and maintaining the Dow Jones Industrial Average were, due to a software bug, having trouble keeping up with the average. And it happened to be a poor trading day, which meant the average was going down, but the computers weren't keeping up with it. And so it looked like a fairly slow decline throughout the day. Eventually, someone discovered that there was a problem, and they failed over to the secondary computer for monitoring the average. It quickly brought the average up to date, which brought the system back into sort of an equilibrium. But the unfortunate part is that this meant that as far as the investors could see, the average, which started out pretty good, declined slowly, spiked downward several hundred points in a period of about 2 or 3 minutes. This made the investors very unhappy, and they increased their sells, which caused the market to go down even further. So when distributed systems fail in this way, it's not just annoying, it's actually expensive. People lose a lot of money when this kind of thing happens. Then there was a malfunction in San Francisco, where a network operator disconnected the connection between the trains and the central routing station as he was preparing to transfer to a new switching station. And so as a result, the central train system couldn't figure out what to do, and so the trains all fell back to their fail-safe mode, which is sit still on the tracks. So there were no train collisions, but for a period of about 30 minutes during rush hour traffic in San Francisco, there were 8 trains worth of people stuck on the tracks, couldn't get to work. So again, time is money, and this is a big deal. Then there was a glorious outage of AT&T's long-distance switches in 1990. Whenever the long-distance switch received a particular signal, the long-distance switch would reboot. In and of itself, that's a fairly benign type of failure. The problem is that when the switch rebooted, it would send this same particular signal to all of its neighboring long-distance switches, causing them to reboot. And of course, this provided a very cascading failure, which left large portions of the country without long-distance service for a period of many hours before they were able to roll it back to a prior firmware version. There's plenty of cases where distributed systems aren't properly configured for the load they might expect. In the lower case here, the FAA took down the Atlanta Center for Routing Flights and redirected all the traffic to Salt Lake City, which couldn't handle the load, causing hundreds of cancellations and delays of flights. And in the top case, the LA County's main hospital brought online a new central computer. This central computer, this new one, couldn't handle the load, and so the hospital became unable to perform diagnostic tests until they got the old system back online. This meant that doctors couldn't get results. They had to diagnose patients by just looking at them, and they had to reroute ambulances from the LA County main hospital to other hospitals in the area. And then, of course, 2007, Skype had an outage when a major nameless software operating system provider released on a certain Tuesday of every month a set of software patch updates, which this software company's users all downloaded and ran at the same time. And then they rebooted their computer. This caused a very large churn of users of the Skype system. And the protocol was not designed to handle such a sudden, large change in the number of people. And so the joining protocol, which requires them to communicate with a certain set of established peers, was unable to complete. And so Skype had many millions of users who couldn't talk on the phone for, I think it went on for a couple of days before they were able to get the protocol fixed. So these are problems that do occur in distributed systems, in deployed distributed systems. Some of them might have been preventable. Others of them, some of them are hard to prevent. Some of them, you could have prevented fairly easily. But what we want to do is we want to draw attention to these kinds of problems so that we can look towards building new systems with new tools that will help us to avoid these problems in the first place. So, in order to do so, I need to introduce you to the canonical distributed systems developer circa last year, and that's Fred Flintstone. Fred Flintstone is our favorite Stone Age distributed systems developer. He's been at his job for a very long time. He has a lot of practice and experience in building distributed systems, and he's gotten quite good at it over the years through hard work and practice. So let's talk about how it is that Fred builds a distributed system. So first, he has to choose a programming language for his distributed system. And using these technologies, he essentially has to choose between a programming language that gives him good performance or a programming language that makes it easy for him to build his distributed system. Now, Fred, being overly concerned with the performance of his distributed system, is going to pick a fairly low-level implementation language like C++, which will lead him to an unstructured implementation. And by unstructured, I mean that the code is sort of haphazardly placed in a wide variety of files in the source code directory, and there's sort of no rhyme or reason to how it's put together, making it hard to understand. He then takes this implementation and he takes it over to a small LAN where he does some testing. And because he's a good coder, with a few small tweaks, he's able to get this implementation to work. So he's happy, right? He takes this implementation, it's now a working implementation, and he takes it to the internet, ready to run it on the internet. But when he runs it on the internet, he finds that sometimes it works, but occasionally it fails, and oftentimes it's slow. And so now he has to debug this distributed system, which works on the LAN, but not on the internet. Now, in order to do that, he's going to use the state-of-the-art debugging techniques for distributed systems. Namely, he's going to stick printfs in his code. Right? For distributed systems, this is basically as good as it gets. So, when he adds printfs, right, he can't reproduce it on the LAN because the LAN is not a large enough scale to exhibit the problem. But when he's added this logging, he can't reproduce the problem on the internet because the logging has added too much overhead. So he faces this problem where he can't debug the system adequately on the internet, he can't debug the system adequately on a LAN, and so he needs some other techniques. Currently, what Fred does is he continues to deploy it. He waits for users to report problems. He listens. He reasons about the reports that he gets, and he updates the code accordingly. So my research, Mace, that is to bring in a new era of distributed systems programming. So we take Fred, who uses something like C++, and debugs his systems manually using sed and awk. And through the use of Mace, I'll now introduce you to today's high-tech programmer for distributed systems, George Jetson. George is our space-aged distributed systems developer, and he's going to be using the Mace programming language, which will give him C++ performance and high-level features that'll make it easy to build this distributed system. Now we look at the life cycle and how it changes from the way Fred built his distributed system. So George is of course going to be using Mace, which will give him performance and simplicity. This will then lead to a structured implementation, which is easier to see, to understand, and to allow tools to process. He'll still do small-scale testing on a LAN, and once it works, before he runs it on the internet, he's going to do some model checking of the implementation, which will allow him to correct a large set of the corner correctness cases which would have plagued his implementation on the internet. Now he takes his newly corrected implementation out to the internet and runs it, and it usually works. This is still the internet. It's still a distributed system. Things will still go wrong. We're not probably going to be able to correct all of the problems in advance. So Mace allows you to use automated path flow debugging and automated logging, which it provides as extra tools and facilities to help you out once you get to this point. So the types of research that I've done, first we built the Mace programming language. We have used it to implement more than 10 different distributed systems of a wide variety of classes. Each of these distributed systems is shorter and at least as fast, if not faster, than the original implementation proposed in the papers. The Mace language allows you to expose the high-level structure of your distributed system. We've had it publicly available for 4 years in an active user community around the world. Then we've implemented the Mace model checker, which we can use to test unmodified implementations of Mace distributed systems. It's the first liveness checker that can test systems code. So a liveness property is something we'll get to in a minute, but basically it's the idea that you don't know at any given point in time whether or not you have encountered a bug. You only know after looking at an entire execution. We then use it to find the critical transition, which is the transition along the entire execution where the system entered a dead state, a state from which it cannot recover to a live state. And we've used it to find more than 50 bugs in our own implementations. And then finally, we use the PIP path flow analysis tool with Mace to provide causal path tracing of your distributed system, of a deployed system. We've used it to analyze actual executions of our distributed systems and used it to find 17 performance and correctness bugs in Mace implementations. So to give you some context for the types of systems that we're building, we'll talk briefly about a distributed hash table and what it is. So a distributed hash table, like any hash table, is a table that maps keys to values. In order to make it be a hash table, we hash each key, and we use that key value, that hashed value, to tell us which bucket we wish to store each key value pair in. Now, of course, with a hash table, when you want to look up any value for a particular key, you hash the key to find out what bucket to look it up in. You go to that bucket in order to retrieve the actual value from the table. Now, to make it a distributed hash table, we'll take these buckets and we will distribute them out through a network of computers. We'll put them all on different computers connected by a network. And of course, we need to worry about a wide variety of things that can go on in this sort of distributed system, right? So first, we want to worry about the case where nodes might come and go, where they might fail. And so we'll replicate the data at other nodes so that if the node does in fact fail, it can download a cached copy of the data from peers in the distributed system. Also, we're going to run this on the internet, so we need to worry about the fact that nodes will come and go in perhaps quite large quantity. And as nodes come and go, we need to rebalance the data so that it is shared across all of the nodes in the distributed system. Now, because the system might grow quite large, we also need to have a set of routing tables, a method by which you can find the bucket that you're interested in very efficiently rather than looking at all of the nodes. You don't want to sift through 100,000 nodes of a distributed hash table to find the one node that has the data that you care about. So the routing table state will allow you to locate the node that has the bucket quite efficiently. Let's consider now how a query is processed through the distributed system. Suppose that the node on the left-hand side of the slide wishes to look for the value for the key 3. It constructs a message that asks for this value, and it uses the routing table to route this key to the node which is storing the bucket for the key 3. That node will then respond with the answer, well, the value for the key 3 is 9. This is how the programmer has envisioned a distributed hash table and how he's programmed it, how he expects it to work, and under many circumstances, it's how the implementation will work. But let's consider a few scenarios, right? First, suppose that this node in the corner fails. When the node in the corner fails, it will lose its state while still being a node for the bucket 0. Now, of course, the designer expects that he will download a cached copy of the data from his peer prior to receiving any queries. And if this happens, everything will work fine. The query will ask for 3, the response will be 9. But suppose instead that the query arrived at the destination node before the cached copy. A naive implementation of a distributed hash table might incorrectly respond that there is no value for the key 3, simply because it hasn't downloaded that data yet from a peer. So what this means is that in order to get the implementation correct, we have to consider the orderings of all of the different messages that are going around in the distributed system. This isn't the only kind of problem, of course. Another problem occurs when the routing tables aren't properly initialized. In this case, the query may eventually still succeed, but only after traversing through an additional set of hops, which will cause higher latency. From the operator's standpoint, however, he can't tell the difference except that the query took longer. He issued a query, and some abnormally long time later, he gets back a response. But what caused that anomaly? Is it because the routing tables weren't correct? Is it because there was a lot of congestion in the network? The operator doesn't have the visibility to see what's going on. And in a very large distributed system, even the distributed system, the person who's maintaining it, has to visit each node individually to trace the message, and then only if there's enough logging to be able to enable that tracing. Of course, another type of problem might occur if there's a bug in the protocol and a routing loop occurs. If a routing loop occurs, you may issue a query, and it may sift around in the network indefinitely. Now, the query hasn't failed, right? If I checked, if there was some way to check on the query, I could see that the query was still pending. But I'm not getting a result. Well, what do? Do I reissue the query? Do I cancel the query? Maybe it's the case that tomorrow the bug is somehow mysteriously corrected, in which case the query may eventually proceed to its final destination, and I get back a value that I've stopped caring about 2 days ago. Okay? So all of these kinds of problems can and do occur in distributed systems. We have to worry about bugs in the protocol. We have to worry about timing issues. We have to worry about the ways in which the state gets initialized. So with this context, I'll now talk to you a little bit about the programming language that we've built, as well as the model checker, and then if we have time, some of the pip path flow analysis tools. So for the Mace implementation, we're going to be thinking about the system as a layered system, right? We take the DHT application, DHT is the distributed hash table application, and we'll break it up into a set of layers. The top layer is the application user interface layer. So this is the application asking for values or asking to store values. Now, beneath the application user interface layer is the storage layer. So this layer is going to handle storing the data, caching the data, sharing the data with peers as peers come online and go offline. And so that's what it's going to be responsible for, is the data itself. It isn't going to worry about the structure of the system. The structure is the overlay network, which is what's being described by a protocol called pastry. So the pastry protocol organizes the nodes into a geometric structure, the ring, as well as a set of routing tables that allow you to jump across the ring to other nodes close to the node that you're trying to locate. Now we will implement the pastry specification, which was originally published in Middleware 2001, as a finite state machine. So we look at each node individually, and we will imagine or envision the state machine that implements this node. So in this case, we have a set of states and a set of transitions. There are 4 states, 4 high-level states. There's the initial state, the pre-joining state, the joining state, and the joined state. And then a set of transitions, which is given the state that you're in, when an event occurs, the state that you transition to, as well as the side effects that you execute. So we'll think about implementing all of our distributed systems as state machines in this fashion. Of course, we'll have low-level states as well, which you can store to maintain extra information, such as keeping track of the peer that you're joining. But this is how we will implement things in Mace, how we'd like to implement things. So how does it look when Fred decides to implement things, right? I've done plenty of these implementations myself, and I have to say, when you get done with the implementation, the unstructured implementation in C++, it ends up looking a lot like spaghetti code, right? So why is this? This is because you have to implement the data structures, where you're maintaining the peer state. You have to implement the node state, where you're keeping track of your own state. You have to implement the messages and all of the methods that go along with messages, such as printing the message when you want to do debugging. You have to implement the event handlers. When an event comes in, you have to implement the code which calls the handler that you want to execute. There's the dispatch, which is figuring out which event has arrived and figuring out which event handler you want to execute. There's the serialization code, which is taking the messages and any structures that they require and being able to format them such that they can be sent on a network communication channel. Then there's the logging that you insert so that you can debug your system. And this can actually sometimes be another 20, 30, or even 50% of the code just in printfs. Then there's the notifications. The pastry layer has to notify the storage layer whenever nodes come and leave so that it can rebalance the data as appropriate. And of course, this is all in addition to the pastry algorithm, which is what we were trying to implement in the first place. So we'd like to avoid doing all this extra tedious work and focus instead on the algorithm. Now the way we do this in Mace is by providing a high-level state machine representation along with an interface definition. So the interface definition is much like any interface, like a Java interface. You specify the set of methods that this service provides. We call them downcalls. And then the high-level state machine representation, which says when I receive a particular event, here is what I'm going to do. You take these two inputs, you pass them to the Mace compiler, which will output three things. First, a high-performance implementation in C++. Second, a set of debugging and testing hooks. And third, an annotated structure of your system. Now we'll take the first of these, the implementation, and link it together with your application, your user interface. And this can immediately be run on the internet. We'll take the annotated structure and pass it along to a set of visualization tools that can take advantage of the structure and show you what it is that your system is doing. The Mace model checker will use all three of these pieces. It will run the unmodified implementation, it will interact with the implementation using the set of debugging and testing hooks, and then it will make sense of what it's doing using the annotated structure. And finally, the pip path verification tool will use the implementation and the structure to understand what it is that's going on. To implement a system using Mace, you essentially fill out this template. So at the top of this template is the architectural information. So this includes all of the layering of your service. The pastry layer is beneath the storage layer and on top of the transport layer. So this is to say that pastry, which is the name of the service, provides the overlay router interface and uses as a lower level service a TCP transport. Then there's a set of generation options, which are flags to the Mace compiler to tell it to turn on and off certain automated logging features or include other files in this implementation, that sort of thing. Then there's a set of type definitions, which among other things include the set of messages that you're going to be using. Now what's important here is that to define a message in Mace, you essentially define a struct. You need not define any extra fields, any constructors, anything like that. This code is very meticulous and monotonous and is roughly the same code every time by substituting variable names and types. So the Mace compiler can automatically generate these implementations for you, and will. Next comes the persistent state that you store. This includes a set of constants, a set of the high-level states that we talked about, a set of constructor parameters, and any other variables that you maintain from one event to the next event. And then finally is the execution portion of your service. This is the transition arcs, how you get from one state to another state. So by filling out this template, you can implement a service using Mace. So this slide is giving us a sampling of some of the systems that we've built using Mace, as well as where they were originally published, a comparison of the lines of code of our implementation to the original implementation by the authors, and finally a speed category. Speed has been normalized such that bigger is better. For different services, it might be latency versus bandwidth. So in some cases, bigger or smaller, but it's been normalized to give you some relative experience here. So these systems span everything from overlay protocols to consensus protocols to file distribution protocols to network location protocols. And as you can see, none of these papers were written by me. So a side effect of having done this research is we've gone out and we've reproduced the research that other researchers have also done in order to provide this sort of missing link in a lot of systems work, which is reproducing other people's results. In each of these cases, our implementation, which is the George Jetson implementation, the blue implementation, is shorter and faster, and certainly no longer. And in terms of speed, for most of the implementations, it's faster. In some cases, it's no slower. So this gives us some confidence that our language, our toolkit, our libraries are high performance, are expressive, and are in fact quite effective. Some of these implementations were also done quite quickly. The Bamboo implementation, for example, we did in a matter of 2 days. That includes building and testing. So we're very happy with this Mace implementation. Are there any questions about the Mace programming language, the toolkit, anything that we've covered so far? Okay. So moving on, we'll now talk about the Mace model checker. So the Mace model checker we'll focus on a particular protocol that we tested using the Mace model checker. And we'll talk about pastry. This is the same example we were talking about from before. Importantly, pastry maintains a set of pointers to successor and predecessor nodes. In doing so, it creates this ring. And the ring is critical to the correctness of pastry. If the ring is correct, then a lookup in the DHT will eventually find the correct node based on the implementation. So this is what pastry needs to maintain as a correctness property. Of course, it's not always going to be true because when a node first joins the network, the ring won't exist. Now, pastry does handle things like node departure. So if node A wishes to depart the network, he goes offline. Nodes B and F are responsible for detecting and recovering from node A's failure by correcting the successor and predecessor relationships. It also handles node arrival. Suppose node A comes back online. It's going to send a join message to a bootstrap peer, which in this case is node D, who will forward the join message to node A's closest peer in the network. That's node F. And that's because node F needs to be node A's predecessor. Node F will then respond to node A saying, I'm your predecessor, and node B is your successor. Finally, node A will tell node B and F that it is online and ready for operation. At this point, it is now rejoined in the network. So the pastry protocol handles node departure and arrival, at least most of the time. We found as we were testing our implementation that sometimes when node A tries to join the network, it's unable to join the network. Perplexed by this, we went to the logs to try to figure out what was going on. And the only notable thing in the log was this warning message. Warning, I tried to do leaf set maintenance, but the leaf set was empty. Now, without having to understand the details of the protocol, leaf set maintenance is a periodic action that tries to correct the successor and predecessor pointers. And until the node is able to join, it makes sense for the leaf set to be empty, because you have no successor and predecessor. So in this case, this warning, though it does indicate a problem, is not helpful to figure out what the problem was, or why the node was unable to join. So Fred, in his implementation, tries to solve this problem by adding logging, by trying to reproduce it on the internet, in a LAN, and he's unable to track down the problem using these tools. George says, hey, I've got an idea. This logging thing isn't going to work out, so we should use model checking. Now, model checking in this context is going to be systematic state space exploration. On the left-hand side of the slide, we're showing the state of the system. That includes the state of the two nodes, as well as the state of the network. And on the right-hand side, we're showing the portion of the state space that we have explored thus far. So we start from the initial state, which is we've just booted the two nodes, and there are no messages in the network. We can either initialize node 1, or we can initialize node 2. These are the only two things that can happen on an execution of length 1. And doing so, we have explored the entire state space of length 1. We'll now proceed to explore the state space of all executions of length 2. After initializing node 1, you could reset node 1. It could reboot. You could initialize node 2, or node 2 could receive a message that was sent by node 1 in node 1's initialization step. There's a similar set of options had you initialized node 2 first. And having done this, we've now explored all possible executions of length 2. Now, of course, you can see that as the execution length grows, the state space will expand exponentially. So we will not be able to systematically explore the entire state space of a system like pastry because the state space is far too large to do systematic state space exploration. So instead, we want to think about this problem. What is it that we're doing? We're trying to produce symptoms. That is to say, we have an implementation of pastry and we have a symptom. The node cannot rejoin. We'd like to pass these two things to the model checker and have it output an execution that exhibits the symptom. So with existing model checkers that can test systems code, unmodified implementations, they can only test safety properties. So a safety property is, roughly speaking, a set of executions satisfying always P, where P is a state predicate. So for example, an assertion is an example of a safety property. Whenever the program counter reaches the line of the assertion, the property must be true, otherwise you've experienced a bug. So let's try having our symptom be a safety property. Right? If the nodes always form a ring, this will not be a safety property. The model checker will return instantly because right after booting all 6 nodes, they will not be in a ring. A safety property is something that must always be true. So this cannot be a safety property. All right? So maybe it's the case that if I have a successor, the successor's predecessor should be me. Seems like a sensible safety property, except that in a distributed system, we have asynchrony. And there's going to be some time differentiation between when I set the predecessor on one node and the successor on the other node. This, too, is not a safety property because it's not always true. Similarly, the fact that nodes should always have successors is also not a safety property. Aha, we say, here is a safety property. The join timer should always be scheduled. Suppose that initially the join failed because the network dropped the message. And I didn't retry the join because the join timer has become unscheduled. So we write this as a safety property, and we pass it to the model checker. And we run the system, and we wait, and wait, and wait, and wait. In this particular case, this is not related to the bug. The bug was not that the join timer became unscheduled. So we need to do something else to try to find the bug, and this finding it in this mechanism sort of suggests that we have to have some idea of what the bug is before we can use the model checker to discover an execution violating it. What we'd like to be able to do is to specify a liveness property. So a liveness property is essentially always eventually P, or basically eventually something should always happen. In the case of pastry, eventually the nodes should form a ring. In the case of a file distribution protocol, eventually all the nodes should receive the file. So, nodes forming a ring, that's a liveness property. Node pointers being symmetric, that's another liveness property. Nodes having successors, another liveness property. We want to be able to specify liveness properties. So why can't we do this using existing model checkers? Basically, the problem is this. If you start at the blue state as the initial state, and you exhaustively explore the gray rings, if you exhaustively explore the state space around the initial state, you may discover some violations of known safety properties. But what can you say about all of the states that have not violated any safety properties? You're not likely to have any states that reach the liveness properties because these may take hundreds of steps in order to reach, where you will not probably be able to search more than 30 or 40 steps exhaustively. So what can you say about these properties? Are they bugs? Going in and looking at each one independently is going to be a huge overhead, and you're not going to want to, especially given that most executions from the periphery of the state space you explore will, in fact, eventually reach the liveness properties, the live states, if you let them run long enough. On the other hand, you may have an execution that runs on and on and on and on and on and never reaches a live state. So here we're going to hypothesize that there's some dead state region, some dead state space, that once you enter the dead state space, you cannot escape from it, right? Once you've been buried, you can't crawl out. You're dead. And we further recognize that just before entering the dead state space, the execution could have gone a different direction. And having gone a different direction, it could reach a live state. So how can we use this to augment model checking to find liveness violations? Well, what we do is we start with the initial state, we run a random execution. If the random execution reaches the live state, then we haven't encountered any bugs so far. We haven't encountered any dead states. So then we exhaustively explore up to some depth, and every state that we encounter, we run another random execution. We continue this process until eventually we've come across a state that when we run a random execution from that state, it does not reach the live state space, despite running for an order of magnitude more steps than any of the other executions. We suspect this might be a bug. And now we proceed to try to figure out where along this execution the bug is. Unfortunately, it's an 80,000 step execution and a 2 gigabyte log file. Now, I spent a few hours trying to sift through one of these log files to try to figure out where the bug was, and I grew tired. You don't want to debug your system in this fashion. So we had to develop another technique to figure out whether or not there was a bug, and if there was a bug, where the dead state space was found. The solution, however, is quite simple. You take a prefix of the execution, and you branch it. You run another random execution from that state. If you reach the live state space, you know that you haven't entered the dead region yet. You now grow forward exponentially until you find a state that when you do branch, a step that when you do branch, no matter how many executions you run, 40, 80, 120, none of them reach the live state space. Now, this is not a guarantee. It's a heuristic, but it's an awful good one. We haven't had any failures in this case. So we'll hypothesize that this is a dead state space. And now we can use a binary search to isolate down to the one state where before that step we have proof, we have a path that reaches the good state space. And executing a single event into the future just one event, one delivery of a message, one execution of a timer, or one application request, no matter what we do, having run hundreds of executions, none of them reach the live state space. At this point, the model checker says, I believe there's a bug, and I believe the bug is related to whatever happened in that step right there, the critical transition, the transition from not being dead to being dead, from just being sick to being dead. Okay? Now, I mentioned the fact that we haven't had any errors. What I mean is we haven't had any cases where there was a critical transition identified and there was not a bug. The critical transition has been off by a few steps, up to 4 steps in the experience that I've seen. But 4 steps, that's enough for a programmer to look at and say, well, it could have happened in this range. So that's our experience with the critical transition. So we take this technique and we apply it back to the pastry bug. Now remember, of course, that in addition to the ring that pastry is maintaining, there's the routing tables, and they'll actually be important in understanding the bug. We run the model checker on pastry, and after running for a while, it outputs this sequence of steps, which includes as step 5 the critical transition. We'll walk through these steps. First, node D, as part of the normal pastry protocol, sends a message to node F, which among other things alerts node F that there is a node called A. This is just normal, periodic, hello, how are you doing, what have you been up to lately protocol for pastry, maintenance. Next, node A departs. Nodes B and F detect that node A has departed and correct the ring in its absence. Node A comes back online, and then, in the critical transition, node F receives the message from node D telling it about node A. At this point, our implementation updated the routing table to point to node A. Now when node A tries to join, remember the goal is to route the message to A's closest peer in the ring. When F gets the message from D, it says, I know a node that's closer to A than myself. It's node A. So I'll forward the join message to node A. Node A receives its own join message and drops it because it can't join off of itself. Now, you might think that this is a simple bug to fix, and maybe it is. It's actually not. But your initial fix might be, well, don't forward a join message back to yourself, back to the node that's trying to join. In fact, we did that just to see what would happen. And what happens is that we find a case where 2 nodes fail, and they try to join, and their join messages are forwarded to each other. So it's not that simple. You have to do something a bit more complicated to recover from this bug. So George is happy. He's found his bug. He can fix his implementation, and he goes over to tell Fred about it. He says, Fred, I found your bug, okay? And Fred says, phew, I've been working on this for weeks, and I've added my debugging, I've run it on the internet, I've run it on my LAN, I cannot reproduce it. So he's happy to have found it, but it's way too much effort. But kidding aside, this message appears in the free pastry changelog for version 1.4.2. Basically what it says is, we found this bug in our system in the sense that we saw it exhibited. We tried for a while to fix it. We stopped being able to reproduce it, and so we gave up. This, I think, pretty much speaks for itself. Mace model checker, manual testing. I'm going with the model checker. So to recap, there's liveness and there's safety. In liveness, you specify the expected behavior, which you should know because it's the system that you're building. The system should do what you expect the system to do. And then it's fairly easy usually to say what the system should do, and you don't have to have any prior knowledge of the specific errors that can occur in your system. On the other hand, with safety properties, you are checking for specific errors. Now, it's a very good way to test for specific errors, but you have to know what the problems are in order to specify them. So the Mace model checker is going to find executions that violate liveness, and critically, it will find the dead states and the critical transition leading to the dead state. We've applied the Mace model checker to many of our implementations. 4 of them are shown here. The first 3 had been well tested and run on the internet without knowing about any particular errors. Not that we hadn't experienced any errors, right? This is a distributed system. If you see a random error, the easiest thing to do is to look at it briefly. If you don't figure out what's going on wrong, you chalk it up to bad luck, some fluke that happened in the network, and you move on, right? So we've been running these systems for years, not knowing that they had these latent bugs. In the last case, in the core implementation, we had done, this was an experiment. I tested it first by hand, and then I tested it using the model checker. I wanted to know, did the model checker find all of the bugs that I could find by hand? So, we found more than 50 bugs, and we found many more since that. In fact, most Mace developers use this as part of their daily testing routine. Whenever they want to test something, they use the model checker. of the liveness and safety bugs, we found more liveness bugs than safety bugs. And actually, that number is artificially inflated for safety because once you find a liveness bug, it will often lead you to writing new safety properties. Right? A dead state is a state one should never enter. So once you've discovered that a state is dead, you can often write a property that characterizes the dead state. So many bugs that we found as safety violations were first learned that they were problems because we found them using a liveness property. These three, as I mentioned, were well tested beforehand, and this one I tested by hand. So as I said, liveness violations lead to safety properties, but what I did find by hand is that I found several bugs related to the performance of code, which I couldn't find using the Mace model checker. Because the Mace model checker only cares about whether or not eventually something happens. It has no idea or care what time it happens. Any questions on the Mace model checker? Great, moving on. So talk about performance issues in distributed systems. So what happens is you have this ring of nodes and there's messages and they're flying around all over the place, right? Nodes are rebooting, messages are going everywhere, there's lookups happening in the system, and you're trying to figure out whether or not the system is performing adequately. So what do? In practice, we gather statistics at the end, right? At the end, we look at the stats. There were 1,000 lookups, 8,000 messages. The average lookup was 2 seconds, the minimum lookup was 0.8 seconds. There was a maximum lookup of 12 seconds, but really, I mean, that's probably just a network error, right? I mean, I don't have to worry about that, do I? If I do, that means I have to siphon through all of the logs and all of the nodes and figure out what it was that caused that error. Much easier to just say, the 90th percentile, which was 3 seconds, is acceptable. We'll just write off the rest of these cases. And this is what we do in practice. And if we really need the results to be perfect, we just rerun the experiment until the bad stuff doesn't happen in practice. Okay? What we'd really like to be able to do, however, right, so Fred says, look, I'm not going to bother debugging this case. It's too hard. It's good enough for me. But George says, I'd like to actually verify that every lookup was executed the way it should have been executed. Of course, I'm not going to do this by hand, so I need to use automated causal path analysis. So what we do is we characterize paths as either good or bad. So for a lookup path, remember the lookup path from before, node A forwards his lookup to node D, to node E, and back to A. This is a good path. It's a short path. It goes back to the source. On the other hand, one of the bad paths, right, so that's what the path is going to look like, A to D to E, and back to A. On the other hand, the bad path, for example, was when the routing tables were not fully initialized, and you had traversed through B, C, D, and E before you get back to A. Right, so you can actually write a property that says a lookup path should have a height of no more than 4. And thus, if there's a height 5 or 6, it will be flagged by the pip path performance validator so that you can then go back and look at that specific path, pointing you to where in the log file you should look. So how do we do this? We start with the two nodes A and B, or all the nodes. We collect their chronological event logs. First, we identify the messages that the two nodes are sending to each other, and then we break up the log based on event boundaries. Events in Mace are atomic, and so we only worry about when an event occurs. So we break it up into messages and events, and now we can use the happens before relationship to sift this log together into one sort of unified log. Having done this, we'll then split it back apart, of course, and redraw the messages. This gives us a chronological event graph, which is a very, very useful debugging technique. In fact, this is probably the most used debugging technique that Mace provides. And all of this is done automatically. You don't have to do any work to get this graph, except write the system in the first place. Now, to do path flow verification, we'll take this a step further. And we do this by taking the events which are causally related to each other. These are the ones connected by message arrows, and making the paths for them. So, and then once we've collected these paths, the causally related paths, we'll categorize them. So the first set of paths are, the initialization paths or the timer paths, which have no side effects. Then there's the join path, where node A sends a message to node B, and so forth and so on before getting back to node A. And then you have your lookup paths. Okay? So to write your expectations, you have an expectation that the first node in the path is a lookup node. There's a set of forwarding nodes, and finally a destination node, before returning back to receiving the response. So we write this expectation, and we run our implementation using this expectation, and it actually found this path. If you think about that for a second, what you're looking at is the case where the routing table was incorrect. There was a bug in the protocol causing the routing table to be incorrect, but was eventually corrected by, by a spurious message that eventually arrives, and so we correct the routing table. We didn't know this was occurring until the pip tool told us that this path existed. Right? Before, we look at the performance anomaly and we say, don't worry about it. But because of this, we're able to look at the individual paths that cause us problems. So we've used pip, We've used pip to find 17 bugs in our own implementations. This is across 3 different systems: Splitstream, which is a streaming protocol; Bullet, which is a file transfer protocol; and Ransub, which is an aggregation protocol. And it's important to note that the compiler, the Mace compiler, auto-generates most of the annotations you need to insert into your code to use pip. Pip is a third-party system, which I also worked on, but you use it by instrumenting your code with the messages and the event boundaries. But the important thing is that the Mace compiler writes all of those for you. All you have to do to tell pip is you have to say, here's where a path begins. Well, that's really all you have to do. Okay? So these paths are causally related sets of events, which are marked by fine-grained execution tasks. These paths are checked independently, and they give you sort of the ability to do what I think of as sort of flexible safety properties. Right? I want to flag things that are outside my expectations so that I can look at them more closely. And they weren't necessarily bugs, but they're worth additional looking. So these are the kinds of things, and of course pip comes with a great visualization tool as well, to let you see the paths, the aggregate statistics, and so forth. So, in conclusion, and that URL is actually out of date. It's www.macesystems.org. Sorry. Understanding is the key to distributed systems building, right? We're writing systems today that are far too complicated for us to understand. We're dealing with hundreds or thousands of nodes or hundreds of thousands of nodes, sending messages at an incredible rate. And we, as humans, aren't real good at keeping all that straight. So we need tools to help us understand distributed systems. First part of this is the programmers need to focus on the algorithms, not the rest of the tedious details. So we built the Mace programming language, which allows you to do a structured implementation and a domain-specific language that makes it easy to build your distributed systems while focusing on the algorithms. Now, of course, algorithms are still hard to get correct. So we have the Mace model checker, which helps you find errors, bugs in your algorithms, your implementations. And then finally, correctness doesn't imply good performance. So we augment these tools with a set of path verification tools and other tools that we're working on now to try to do path verification and performance testing in order to alert the programmer to any errors in performance. And with that, that's the end of the talk. Are there any questions? I must have been crystal clear. Yes?
This isn't a question, but just a comment. I'm very impressed with what you've written,
Thank you.
in all honesty.
No more errors in your code.
Yeah, so one thing to say, Mace is hard to integrate into existing systems. So if you have a large behemoth of code that you're working with, you probably won't be using Mace. But if you're building a new distributed system from the ground, definitely use Mace. Highly recommend it. I even provide support. You just send an email, mace@macesystems.org, and you'll get a response. Code's publicly available right down to every commit that I make. So, great. Hope you all get to use Mace. Thanks.